This is Dr. Mohan from EC Department of Institute of Aeronautical Engineering. Today we are going to discuss about signal analysis in the subject of signal and stochastic processing. Today presentation outline is analog between vector and signals. Dot product of two vector, signal, orthogonal vector space, mean square error, closed completed set orthogonal, orthogonality in complex function. First we go for the analogy between the vector as well as of signal. We take for the two vector, one is represented as a V1 and V2. If the vector V1, how it's going to active? A vector consists of magnitude as well as of direction. So that's why we represent for the vector for any variable. Suppose we take for the A. So you represent for the arrow mark. So that means the arrow mark is represented as here where the coefficient, that means the A is going to active. This is represented as a right direction. Arrow mark is represented as a right direction. Then A is represented as a magnitude value. So the direction is represented by the arrow mark of the coefficient as well as of the magnitude value is represented as A. Here we need to explanation purpose. I take for the two vector. One is represented as V1 and V2. This arrow mark that is represented as a direction, it may be depends upon the coefficient where it will be going to active, then it will be going to activated. So that's why the vector consists of magnitude as well as of direction we represent. The name of the vector is denoted by bolded space. So what we are going to represent for the bolded value, we represent for this is the vectors. So that's why this is V1 vector, then this one is represented as a V2 vector. The arrow mark, where the arrow mark is indicated, the vector is projected to that direction. For the V1 is going to projected for this direction. So simply we may represent as a bolded place, we make as a vector. Next we go for the magnitude is represent for the lighted place. What they are going to represent? This is I put for the dotted line. This dotted line I consider as a vector. That is, I represent vector in the magnitude value. So now V is a vector with magnitude I call for this V. So this is V1, then the vector value I represent as a V1 here. Okay. So based on this condition, I take for the two vector, consider for the two vector, then V1 and V2 as in the diagram. Next, let us consider V1 with V2 is given by C1 to V2. So this values, what is it? If the vector V1, if I may represent for the case of analogy with vector of V2. So that's why I write as a V1 is equal to C1 to V2. We may represent. So the magnitude is perpendicular to the V2 vector. That's why we may write as a V1 is equal to C1 to V2. The component of vector V1 analog with the vector V2 can be obtained by taking the perpendicular from the end of V1 to the V2. This is represented as an analogy between vector as well as of signal. Now we may go for the analysis of analog vector between the signal. So now we take for the vector of V1 can be expressed in terms of V2. We may represent V1 is equal to C12 plus V2 plus VE. Now V is represented as an error vector. See, now in this diagram, what the V1 is going to have for the some length L. So V2 have the some length, but the vector, if we make to vector, it's represent for the direction, that is V1 of like this direction, V2 of this arrow mark of upper cases. Now we come with the magnitude response. The magnitude response V1 is going to fall with the V2. Now you can compare with this length as well as this length. V2 length of where they are going to fall. It's getting to reduce. So based on the condition, reduced condition, we represent for the some deviation is going to happen. That deviation called for the vector error. We call for the vector error. So that's why while we going to conclude it for the case of the vector in the term of V2, I write as here vector V1 is equal to C1 to V2 plus VE. C12 is represented as a vector coefficient. VE is represented as a vector error due to the V1 as well as of V2. Now the vector error not have the constant, or the vector coefficient is not have the constant, but in this case only the way of expression in the vector V1 in terms of V2, I take for the two different case of vector analysis. V1 is possible to fall in the slanting line of V2, or if V1 is fall for the after the slanting line of V2. V1 is fall after the slanting line of V2. This is also possible for the vector cases. So now we need to analyze it. Both the case we have the two different kind of vector analysis, but it's going to follow for the same analogy function. The V1 is equal to, for in this case of the diagram, V1 is equal to C1 V2 plus VE1. Next, for this case of diagram representation, V2 is equal to C2 V2 plus VE2 we may represent. So this case the error value VE1 and VE2 is entirely different together. So the error signal is minimum for large component value of C12. So that case I represent for the C12 is equal to 0. Then the two signal are said to be orthogonal. If not, the signal is non-orthogonal signal. So now the case of V1 and V2, we make it for the orthogonal function. Due to that case, we consider as the vector coefficient C12 or C1 or C2, that value is equal to 0. So when the falling of the coefficient of vector value is represented as 0, then the signal is represented as orthogonal. If you need to represent for the orthogonal, this is not only the way expression of vector V1 in terms of V2. We may express anyway. Anyway, we need to make as a orthogonality of the signal. That's the main concept to study for this topic. Next, dot product of two vector. When we make for the dot product in the two vector, what will be going to happen? If I am doing for the dot product V1 dot V2, then it's going to produce the output V1 dot V2 cos theta. So see this diagram representation. This the case that this theta value is not have same. Why? Because of this V, that V, the vector, it's maybe happen for any degree. So here have the theta 1, it's maybe have like this one, that is theta 2, it's maybe have for the theta 3, like that will be going to happen. So but all the case we make it for the magnitude, that will be happen the C12, that this C12 is not equal. That's why we taken for the orthogonality function of C12 is equal to 0. So due to that case, we may go for the dot product of two vector. The V1 dot V2 is equal to V1 dot V2 of cos theta. Now the theta is represented as an angle between the V1 as well as V2. Now the angle value is represented as a very minimum. That case what we going to represent, there is no happen for the C12, that is C12 is not going to happen. So that case I represent as a 0. Then V1 V2 is equal to V2 into V1 or V1 into V2. We may represent the component of V1 analog n. We represent as a, that is represent for the analog is we call for the analog is represent as a angle we make for this mean. So what we represent for the analogy, we say for this is analogy when the orthogonality function. Now theta value is going to have minimum. Okay, theta values represents minimum that we call for the analogy or analog. V2 the case V1 analog V2 we represent as a V1 cos theta. So because of its the theta values we have for the minimum cases, that value is equal to V1 V2 divided by V2 we may represent from this equation. So from this equation V1 V2 is equal to V2 into V1. So now I represent as here V2 is equal to V1 cos theta, that value is equal to V1 V2 divided by V2 I may represent. From the diagram component of V1 analog V2, that value is equal to C1 to V2 we may represent. Now we need to substitute for this value into this portion. V1 dot V2 divided by V2 is equal to C1 to V2. We represent as say V2 is equal to C1 to V2. Then you can substitute after the substitution. I need to take for the magnitude value of C12 is equal to V1 dot V2 divided by V2. Now the dot product, if we make for the dot product, it's going to produce the output as a magnitude coefficient, that is called for the C12, that value is equal to vector of V1 V2 divided by the vector of V2 we may represent. This is represented as a dot product. Then we go for the signal. The signal in the vector analysis, orthogonality can be applied to the signals. We consider for the two signal, that is represents a F1 and F2. Both the signal is depends upon the time period. So that's why I represent for the simple vector case. We may approximate for the both F1 and F2. I should write as a F1 of t as well as of F2 of t I may represent. So why? Because of both the signals are time based signal. Now if we take for the time based signal, I should write for the time based signal as per the vector orthogonality. I should make as a F1 of t is, now the signal is represented as a time based F1 and F2. Then here I write as a vector based, that is we represent as a F1 of t as represented as a vector. But compared to the F of t, this is a time based. Based on the time, the signal amplitude is getting to vary. But this one is based on the time, the signal amplitude is getting to vary, even though direction also is possible to apply to that. That's the condition. We write for the F1 of t is equal to C1 to F2 of t plus Fe of t. All the term, you see for the all the term, it's all in based on the time period, even though it's based on the vector also. Here, the time of Fe of 2, or it's represented as a vector. So now I consider as here the F1 and F2, we put for the two time interval, that is represented as a T1 lesser than of T lesser than of T2, because of we take for the two signal F1 as well as of F2. But this two signal, the time interval between the T1 and T2, because we analyzing for the time based, then that case the error value, the signal error value is represented as a Fe of t is equal to F1 of t minus of C1 to F2 of t. We modified for this equation as the case of the error value. This is a signal error value. So this is the way we make to represent for the signal as the vector coefficient. So the vector coefficient Fe of t in the error condition, F1 of t minus of C1 to F2 of t. If or once the possible way of minimizing the error is integrated over the interval of T1 and T2. So we taken for the interval of T1 and T2 interval, that is represented as average value. We make to take for the average value. What is the average value? Because of T2, T1 as well as of T2. That is 1 by T2 minus of T1, integration of interval between the T1 and T2, what the error is going to happen for the both the signal F1 of t as well as of F2 of t based on the differentiate with the dt. It's represented as a minimization of error. Now we know this Fe of t. What is it? We find for the Fe of t is equal to F1 of t minus of C1 to F2 of t we write. Then we substitute for the value to here. So the minimized error value is equal to 1 by T2 minus of T1. This is average of signal interval between the T1 and T2. The integration of T1 and T2, F1 of T minus of C1 to F2 of T dt we may represent. This is the way we may reduce the signal error if we take for the two different kind of signal. If we make as a orthogonality in the signal condition, then this step also does not reduce the error to applicable per extent. This can be corrected by taking the square of error function. We know the square of error function. What is that? We need to take for the magnitude value in the square. So this case I represent for the error value, minimization of error value, epsilon is equal to 1 by T2 minus T2 integration of T1 T2 Fe of t whole square dt. Now we apply for the Fe of t. We know the Fe of t, that Fe of t is represented as the signal as per the case of here F1 of t minus of C1 to F2 of t dt we may write. This is represented as F1 of t. So 1 by T2 minus of T1 integration of T1 T2 F1 of t minus of C1 to F2 of t whole square dt I should represent, where E is represents a mean square error value of signal. Then C12 is represented as a minimization of the error. Now, if you need to minimization, you must take for the differentiate with the coefficient. Now, due to minimization, I should take for the differentiate with the vector coefficient C12 d by dC12 of what the error value is going to receive from minimization of signal, I should apply for here. That value is equal to 0. Now, this case, I should write for the minimization of error d by dC12 of what we are going to receive, that is represented as Fe of t. We may represent this value is equal to 0. It's condition of minimization in the vector case. D by dC2 1 by T2 minus of T1 integration of T1 T2 F1 of T minus of C1 to F2 of T whole square dt is equal to 0 for this case of minimization error condition. Then after we may d by C2 is going to put for the inside of our equation, where the dC1 d by dC2 is going to dC2 is going 1 2 is going to have, there only is possible to do further differentiation. Remaining things are represented as a zero state condition. So we may insert further d by C12 for inside the integration. So then we take it out for the 1 by T2 minus of T1 integration of T1 T2 d by dC12 F1 square dt minus of d by dC2 2 time of F1t C1 to F2 of t plus of d by dC2 F2 square f of t c square 1 to d of t is equal to 0. Now, the derivative of term which do not have C12 term are 0. Then I write as your equation, our equation as integration of T1 T2 minus of 2 time of F1 of t F2 of t dt plus 2 time of C1 of t integration of T1 T2 F2 square t dt is equal to 0. Then finally I write as here this value. What is that? We may find for the minimized value of error coefficient. The minimized error coefficient is equal to C12. Then take it out. This one is Also we go, if we go into this side, 0 side is go in the sense that is consist of 2 time of C1 to integration of T1 T2, then F2 of square of T dt I should write. So this minus minus here also minus, this minus getting to cancel, remaining this coefficient we need. Then what we are going to C12, this 2 both 2 getting to cancel. C12 is represented as a integration of what the value is present, integration of T1 to T2 F1 of T F2 of T dt divided by integration of T1 to T2 F2 square T dt we may represent. Component is 0, then two signal are said to be orthogonal. Now, we may put for the C12 equal to 0 to get the condition of orthogonality. Now, this is a minimization. For C12, we make it for the minimization. Then only possible for the two vector is represented as orthogonal. Then I represent as C12 is equal to 0. Then C12 is equal to 0. Then what will be happen? The integration value, that is the upper limit, denominator as well as a numerator, that is equal to 0. Now, this value, this denominator value is represented as 0. Then integration of T1 to T2 F1 of T into F2 of T dt is equal to 0. So, this is the condition the signal is represented as orthogonality. There is no vector coefficient is present. Then both the signal is represented as F1 of T and F2 of T, both is represented as orthogonal. Both of them have the equal coefficient, or both of them have the same characteristics we may represent. This equation is going to be factored together. This is a way we are making to represent for the signal analysis. Next, we go for the orthogonality vector space. The vector space not only happen for the only one direction. It may be possible to do for the 3 direction also, that is x, y as well as z direction. Previously we studied for this, all the vector is represented as only one direction. Whether to take for the v1 from this diagram, I take for this diagram, the v1 is going to doing for the some direction, v2 is going to have the some direction. So it's not have for the same direction, it may be have for the 3 directional also, whether it will be have the x, y, z. So this is only one direction is going to happen. You have the x and the y. So this direction I represent as a v2 of vector I represent. So then the vector, its multiple direction is going to possible. Why? Because of we go for the dot product case, that is a theta also is going to present. Due to that case, we may go for the multiple direction. So that multiple direction we consider only for the 3-dimensional vector space. That is represented as a orthogonal vector space. Here, complete set of orthogonal vector is referred to as orthogonal vector space. It's considered as for the 3-dimensional vector space as shown in figure. So in this figure, I take for the 3-dimensional case, the vector I represent for the A. This A, what will be going to, it is going to infer with your x direction, y direction and z direction for any one of the case. That's it. For any one of the case, for you take for the y and x, that y and x where will be going to happen. So the y I take for the in this y, any one of the point, that is represented as y1. Then x I take for the any one of point is represented as x value. Then z direction, any one of the point I take for the z1. I need to match, I need to meet all the points simultaneously. Then I make it for the magnitude value. This is a magnitude value. So these are the vectors x, y, z. It's maybe how the different direction is going to happen. Those case I put for the magnitude value, that is represented as it's going to meet for the A point. That A point I consider with x1, y1 and z1. So now finally I write as A of x1, y1, then z1. I should write. This point is represented as A point is going to meet for all vector values we take for the different case of direction. That will be we consider as a 3-dimensional vector space. Now the vector space A at the point I represent as a x1, A x1, y1, z1 I represent. This 3-unit vector we may represent for the Vx, Vy and Vz because of we taken for the vectors. So that is Vx, Vy and Vz we may represent. Those direction is called for x direction, y direction and z direction respectively. Thus unit vector are mutually orthogonal. We consider it satisfies the following condition. If mutually orthogonal, what will be going to happen? Vx, Vx equal to Vy, Vy equal to Vz, Vz equal to 1. Or if we go for the different direction, that is Vx, Vy or Vy, Vz or Vz, Vz, Vx is equal to 0. So this is a portion we may take for the orthogonality condition. So we study for the orthogonality in the vector space or signal space. What is it represent? We multiply with the f1, f2, two signal, integrate with the time interval t1 and t2, dt is equal to 0. Same the condition if the signal is orthogonal in the different direction, the Vx, Vy that is represented as a two signal. Okay, two signal that is two different direction. Two signal, two different direction Vx, Vy is equal to then another two signal we take for the Vy, Vz and we take for the another case Vz, Vx that value is equal to 0. But in the case of within the vector because of there is no direction present from the our signal, that's why the theta value is equal to null. So in if that case, if we take for the signal is present for the same location, that is Vx and Vx, that both will be have the same location of the dimension in the xy direction. Here only, if we take x in the sense, here only are the two signal. That case equal to represent as a Vx, Vx equal to Vy, Vy equal to Vz, Vz equal to 1. We may represent. So this two case I represent for the mathematically I represent for the VA VO B is equal to 1 when A and B is equal to equal. If A and B is not equal, I represent as a 0. So this equation as a mathematical representation of orthogonality function, I simplify for the mathematically VA and VB. Two vector I take that three dimensional I take for the two vector. Those direction is equal to 1 when A and B are equal. If not, 0. A and B are not equal, then that value is equal to VA, VB equal to 0. Now, a vector A can be represented in terms of components under unit vector as A is equal to x1 Vx plus y1 Vy plus z1 Vz. Any vector in the three-dimensional space can be represented in terms of 3-unit vector only. Now, if the 3-unit vector, what will be going to happen? If you consider for the n-dimensional space, we taken for here as a only 3-dimensional based on the x, y, z direction. We represent for the our signal as a point is represent for the x1 Vx plus y1 Vy plus z1 Vz we may represent. Then, if we have for the n dimensional of case of the signal, that is the case of the signal, if we represent for the value of a point is represented as a equal to x1 Vx plus y1 Vy plus z1 Vz up to how many n's are there, we may take it for that location. So, the component of a is represented as analog x-axis equal to a Vx. The component of a analog y-axis is represented as a Vy. Then the component a analog z-axis is represented as a Vz. Okay. So here, that's why I may represent as each direction we take for x and y and z direction. Now this all direction together, then it's produced for the n-dimensional cases. The component of a along same g-axis, that is analogy, we represent as a Vg we may represent. So that will be going to take for the any direction. Okay. So any direction analog condition. Another condition we take for the any direction, that is represent as a alarm we may represent as AVG. Now, if we take for the AVG condition, then I consider as a C is represent as a what they are going to get for the different direction of n position in the first vector. That is, I consider as a C of G. Then x1 Vx plus y1 Vy plus z1 Vz plus up to g1 Vg plus up to n1 Vg. Then we multiply with the Vg, what the direction is going to consist. Now we simplify for this equation. We in we may multiply with Vg in all the coefficient x1 Vx Vg plus y1 Vy Vg plus up to what they are going to have here is in. Then I take for the G1, that is only one direction, the gain value of the signal I consider it as a 0. So since Vg is equal to 1. Why? Because of we taken the condition of like this one. Va, Vb is equal to 1 when A equal to B. If 0 when A is not equal to B. That is orthogonal and non-orthogonal condition. So now what I am doing, if Vgg is not equal to 1, if Vgg is equal to K, I should write. That's the condition AVg equal to G1 Vg is equal to G1 into K. So this K is represented as a VGG we may represent. Finally, we concluded the orthogonality condition of our three-dimensional case G1 is equal to AVG divided by K. The K is represented as our total coefficient, what we are going to getting for the orthogonality function together. That's why finally we represent as one x is represented as only one direction. That's why I represent as gain value is equal to 1. Then I write for the AVG divided by K. A is going to meet for all direction of our signals in the only one position as a x position. So this is the way we may represent for the three-dimensional signal analysis in the vector space. Next, orthogonal signal space. Now, in this orthogonal signal space, we consider for the n number of mutual orthogonal function. So, within that x direction only going to have for the n number of orthogonal condition. So, the x is consist of x1 to x of n, or y is consist of y1 to y of n, or z direction consist of z1 to z of n. So this case we take for the only one signal, that is represented as a x1 signal. In this, that is x1 x signal, we have the x1, x2, x3 up to x of n. We may participate together in the x of n. Then what will be going to happen? Now the x of t consists of n number of signal is going to specify. That is x of t is present for the up to n split is going to happen. That means all the n signal we consider as a orthogonal condition. So if we consider orthogonal for condition in the sense, we need to analyze. How we need to analyze? Now signal is represented as a x. We split it for the mutually orthogonal in the n cases. So if we analyze, we take for the some interval of time duration, that is t1 and t2. If we take for the t1 and t2 interval, we consider for the two signal. That's so those signal is represented as a x of j as well as of x of k. How to satisfy for the orthogonality condition? If we satisfy for the orthogonality condition in the sense, we know the orthogonality, the case of two time interval, that is integration of t1 and t2 x of j t xk of t dt is equal to 0 when j and k are not equal. That condition be taken. If the j is not equal to k, then orthogonality function is represented as 0 of our x of I, x of j and x of k of signal. It's going to have for the interval between the t1 and t2. Now let us consider for both the signals are equal. We consider for the both the signals are equal. X of j t and x of k of t. Then what be going to happen for this equation as a mathematically the integration x of k square t dt, that value is equal to some constant we taken k of k. Let the function f of t, it can be approximate with the orthogonality signal space by adding the components along mutually orthogonal signal. Now, those signal I write as a f of t. The f of t is equal to, it's multiply with the signal coefficient c1 x1 of t plus c2 x2 of t up to how many we divided for the signal. What we are going to divide up to n signal we are going to divide it. Those signal c of n x of n t plus the error value. As the first case, signal as a orthogonal condition when the vector space error is equal to fe of t we are going to happen. So that error we are going to adding here, that is f of t is equal to c1 x1 of t plus c2 x2 of t plus c3 x2 of t up to c of n. We divide by the signal as a x of n condition. We represent as c of n xn of t plus fe of t we may represent. Now, based on this condition, I should simplify for application as equal to this all addition I make as a summation. So, the summation of r equal to 1 to n, cr of CR XR of t we may represent. Then finally we concluded for the f of t is equal to f of t minus of summation of r equal to 1 to n CR of XR of t. The mean square error value is represented as an average of our error value. This is also we study for previous case of orthogonality condition. The mean square error value is equal to 1 by t2 minus of t1, the interval between our input signal t1 to t2, that is we take for the integration of t1 t2, what the error we received for the x of n, that is fe of t whole square dt. This value is equal to, we know that value, this fe of t, this is represented as fe of t is equal to, we substitute for here, that value 1 by t2 minus of t1 integration of t1 t2 f of t minus of summation of r equal to 1 to n CR XR t whole square dt represent. This is we call for the error value. That value we substitute here. The component which minimize the mean square error can be found by the differentiation. So this is we done for the previous case. The differentiate with the coefficient. So the mean square error value we may differentiate with the coefficient de by dc1 is equal to de divided by dc2, that is error value is equal to up to k position n, k position is equal to 0. Let us consider our error differentiation is equal to 0 as a ck condition. Then you may apply for the differentiation to this equation. So where the c or is going to there, then it's possible to have the differentiation. In that case, all the term do not contain c of k is 0, then our signal we consider as a r equal to k condition. That term remaining all the orthogonal terms are 0. So due to that case, what it will be going to happen? The integration of this equation. So what will be happen for this equation? The equation is consist of where r equal to k we consider as a 0. Then remaining what the portion? Integration of t1 to t2 minus up to f of t x of k t dt is plus 2 c of k integration of t1 to t2 x of k square t dt is equal to 0. Now we find for the c of k. The c of k is present here. Then we find for the c of k. C of k is equal to integration of t1 to t2 f of t x of k t dt divided by integration of t1 t2 x of k square t dt. Now we know those condition is represented as a 0 initial condition. So those condition as a 0 initial condition, this value we found that k of k. So previously we found that is represented as a k of k. Then you make to cross multiply with c of k. Then finally we get for our signal as integration of t1 to t2 f of t x of k t dt is equal to c of k of k we may represent. So now we take for the only one signal for the three dimension, that is x direction only. That x direction we divided by the n number of particle of different signal, that is x1 to xn. Then we make as a orthogonality function. Those case the orthogonality function c of k we consider as a 0 as a 0 or 1, as the case of v of a v of into v of b is equal to 1 or 0, and a is equal to b, then a is not equal to b. This condition, based on this condition, we find that our error value c of k of k is equal to integration of t1 to t2 f of t x of k dt. Now this value, this condition, the signal, if you divide for any case of x, that is a three-dimensional case of x position, the signal considered as a orthogonal state. Next, we go for the mean square error. So, if you have the n condition of, that is n-dimensional signal, we divide for the too many differentiation of subdivision in the signal. All signal is going to produce for the error. Those error we need to make for the average. That average is called for the mean square error. The average of square of error function fe of t is called mean square error. It is denoted by epsilon. The epsilon we know. What is it? The formula is represented as 1 by t2 minus of t1 integration of t1 t2 fe of t square dt. So this fe of t we derived from the our differential term condition. This is fe of t. We find out for the orthogonal signal space condition only the x direction as x1 to x of n, x1, x2 of n, x2 of t up to x of n we found for the interval of t1 to t2. So based on this condition, we go for the mean square error. The epsilon value is equal to 1 by t2 minus of t1. The time interval between the signal is t1 and t2. At the same time, the signal we taken for the fe of t is equal to, we studied for f of t minus of cr of x of t we studied. So this one we may apply for the fe of t. Then what will be going to happen? Now e is equal to 1 by t2 minus of t1 integration of t1 t2 fe of t square dt as a mean square error, and you should apply for here. Then 1 by t2 minus of t1 integration of t2 t1 t2 fe of t minus of summation of r equal to 1 to n cr xr of t whole square dt. So this value we for divided for the too many signal in the x direction in the three-dimensional case, x1 of t, x2 of t up to xn of t we divided. So those case I take for all the condition I should use for the summation of r equal to 1 to n. This is up to 1 to n we taken. So then after we may split for all the integration as per the this square case 1 by t2 minus of t1 integration of t1 t2 fe square of t dt plus summation of r equal to 1 to n cr of square integration of t1 t2 xr of square t dt, then minus of 2 time of summation of r equal to 1 to n cr integration of t1 t2 xr of t f of t dt. We know that cr square integration of t1 t2 xr of t dt is equal to cr integration of t1 t2 xr of t f of t dt is equal to cr square kr. Then we may substitute for here this equation, this value we may substitute here. Then our epsilon value is equal to 1 by t2 minus of t1 integration of t1 t2 f2 f square of t dt plus summation of r equal to 1 to n cr square kr minus of 2 summation of r equal to 1 to n cr square kr. Then finally, I should simplify for this equation. We got for the output as mean square array is 1 by t2 minus of t1 integration of t1 to t2 f square of t dt minus of summation of r equal to 1 to n c r square kr. Now this is c, this value I may to expand for the equation. Then the epsilon value is equal to 1 by t2 minus of t1 integration of t1 to t2 f square of t dt plus c1 square of k1 plus c2 square of k2 up to how many division is going to happen, up to that much we are going to complete it for our mean square error in the signal cases. The above equation is used to evaluate the mean square error. Up to this much I am going to stop my presentation. So today we studied for the analog between the vector and the signal and the dot product, signal, orthogonal space and mean square error. Next class we see for the remaining two cases, closed completed set orthogonal as well as a orthogonality in complex function. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.